I'm Dr. Donna J. Nelson at the University of Oklahoma. I'm filming the lectures for my organic chemistry class. So this is for Org 1, and this is Chapter 1 for Org 1. This is the first lecture for Chapter 1. So my lectures are going to parallel exactly the textbook that I've adopted for this course, and that is David Klein's Organic Chemistry textbook. And so you'll be able to watch these lectures anytime you want. They'll be available. You'll be able to download them onto your own computer, and you'll also be able to take them with you after you finish this course, so that if you need to review any of these lectures for Org 1, say in preparation for the MCAT or for any entrance exam, you'll have them with you if you choose to keep them. You can also download the PowerPoints for these lectures. They will be available, and you'll be able to download the textbook and the student study guide to accompany the textbook. If you really want to learn this material, you'll watch the lectures, you'll watch the videos, and you'll come to class prepared to ask questions about anything that you did not understand in the videos. You'll be able to pause the videos and look up anything that you need to look up in your textbook or in the student study guide. And I strongly recommend that you do that if you genuinely want to learn this material. Learning the material will be up to you. I can give you the resources that you need to do that, but you will have to exert some effort. So let's start this first lecture. This chapter is simply a review of general chemistry, electrons, bonds, and molecular properties. So you will probably have seen most of this already in your general chemistry course. So we're going to study first this introduction, the structural theory of matter, electrons, bonds, and Lewis structures, identifying formal charges and calculating them, induction and polar covalent bonds, and atomic orbitals here in this first lecture. Then we'll have a second and third lecture for this chapter. So organic chemistry, the study of carbon-containing molecules and their reactions. So you'll be able to answer questions like, what happens to a molecule during a reaction? Molecules collide, well, exactly how? What happens when they collide, and in what format and in what arrangement do they have when they collide? Bonds are broken and bonds are made. So here you can see a bond made, oxygen to carbon. We show the movement of the electrons because the oxygen-carbon bond that is formed is made up of electrons. So a pair of electrons has to be donated from oxygen to carbon. So that's how this new bond is made. In the process of this happening, iodide is expelled and it leaves with that pair of electrons. We'll study reactions like that extensively and many others and analyze them in great detail in Chapter 7. So why do the reactions like this occur? You'll need 2 semesters, Org 1 and Org 2, in order to really fully understand this material. But as before, you need to focus on the electrons. We always focus on the electrons in these reactions. How does one distinguish between organic and inorganic compounds? Organic compounds contain carbon. So organic compounds typically make up things like food, clothes, pharmaceuticals, and plastics, but even inorganic compounds such as ammonium cyanate can be used to make organic compounds. So when this molecule is heated, it forms urea, which is typically regarded as an organic compound. In the mid-1800s, it was first suggested that substances are defined by a specific arrangement of atoms. A compound's formula, however, is not adequate to define it because different compounds differ in the specific ways which atoms are bonded together. For example, these two molecules are isomers. They contain the same number of carbons, oxygens, and hydrogens, but they're connected in different ways. Notice here, the oxygen is bearing two CH3 groups. Here, the oxygen is bearing a C2H5 group and a proton. They have completely different molecular characteristics, such as a boiling point of minus 23 degrees centigrade versus a boiling point of 78.4. So that is over 100 degrees difference in boiling points just by moving the atoms around. So you'll need to study these things, and we will, and you will learn this material, or at least it will be presented to you in great detail. Atoms that are most commonly bonded to carbon include nitrogen, oxygen, halogen, and the halides, fluorine, chlorine, bromine, and iodine. With a few exceptions, each element generally forms a specific number of bonds with other atoms in organic molecules. So here, carbon contains 4 bonds, never more than 4. Nitrogen forms 3 bonds in neutral compounds that are organic. Oxygen atoms in neutral compounds where oxygen is not bearing a charge forms 2 bonds, and the halogens are monovalent where they generally form 1 bond, certainly in compounds, in organic compounds that are neutral molecules. How do potential energy and stability relate? Well, the lower the energy, the more the stability. The more stable a molecule is, the lower its energy will be. And so, what forces keep the bond at the optimal length? Attractive forces between positively charged nuclei and the repulsive forces between 2 positively charged nuclei and repulsive forces between the 2 negatively charged electrons. So you have the attraction between the nuclei and the electrons, positive attracts negative, and you have the repulsion between the positively charged nuclei and the negatively charged electrons. So there's a balance there, and it will keep these 2, for example here, hydrogens, very close to this 0.74 angstroms internuclear distance, although there will be some vibration going on, but that's generally the average interatomic distance. A review from general chemistry: protons contain a +1 charge, neutrons are neutral, these reside in the nucleus, and then electrons, each of which bears a -1 charge, populate the orbitals outside the nucleus. The valence electrons are the electrons in the outermost shell, and those are the ones that we'll focus on because those are the ones that react. In carbon, the 2s and 2p electrons contain the valence, the 2s and 2p orbitals contain the valence electrons. So the 2s and 2p electrons reside in the 2s and 2p orbitals. The valence electrons are the ones that are involved in bonding. Here is part of a periodic table. you can see the group numbers for the group A elements. Just look at the group numbers here. These are the numbers that one needs to calculate the number of valence electrons. Here, the number of valence electrons hydrogen needs will be 1, here beryllium 2, and then for boron, carbon, nitrogen, oxygen 3, 4, 5, and 6, fluorine is 7. And so you just look at the group number of the periodic table in order to know the number of valence electrons for that atom. It's sort of simple. For simple Lewis structures, divide the individual atoms using the dots to represent the valence electrons, and then put the atoms together so that they share pairs of electrons to make complete octets. So here, for the larger atoms, the second period, you can see nitrogen now has 2, 4, 6, 8 electrons. That is a filled octet. Of course, hydrogen will not have a filled octet. It has stability when it is surrounded by only 2 electrons. And so that is its filled shell is being surrounded by 2 electrons. So here the nitrogen is surrounded by 5. It bears 3 hydrogens. Each one of those hydrogens contributes an electron to the 2 electron bond. So now we have nitrogen has the stability of a filled octet. Formal charge. Anions have a negatively charged atom. Cations will be positively charged atoms. Atoms in molecules sharing electrons are typically neutral, but they can also be anionic or cationic. To determine the formal charge for an atom in a given molecule, compare the number of valence electrons that it owns based on its bonding patterns to the number of valence electrons that the atom needs to be neutral based on its periodic table position. And this latter one is the one that we were just talking about on that periodic table. So let's look at these two in order to see how one calculates formal charge. Carbon needs 4 valence electrons to be neutral. It resides in group 4. You saw that on the periodic table that we were just looking at. However, here carbon is surrounded by 8 electrons, but it only owns 4 of them. 1, 2, 3, 4, because 1 electron actually belongs to hydrogen in each of these bonds, and here 1 electron in the CO bond belongs to oxygen. So this molecule is the equivalent of this molecule. Instead of showing the 2 electrons, I've just drawn 1 line to indicate 2 electrons. So you can think of them as carbon owns these 4 electrons because it owns 1 electron from each of these bonds. And so it needs 4 electrons to be neutral. That's the periodic table number. Remember, it's in group 4. So this tells you that it needs 4 so that it will be neutral. And you look and you see it needs 4, and indeed it, quote, owns 4 because there is 1, carbon has 1 from each bond. And so the formal charge calculation for carbon tells us this carbon owns 4 valence electrons, and 4 from the periodic table. So you have the periodic table number minus the number of valence electrons, and that gives 0. So you would predict this carbon to have a formal charge of 0. Now look at oxygen. The formal charge here comes from the periodic table. It's in the column 6. Okay, and you look up here and you see that oxygen has 7 electrons. So one comes from the carbon-oxygen bond, and it has 3 lone pairs. 1, 2, 3 lone pairs. That's 6 electrons plus this one. It is surrounded by 7 electrons. It actually has the stability of a filled octet, but it actually, quote, owns 7 electrons because the way that we're calculating this, 1 electron is given to carbon and 1 electron is given to oxygen. And so the 6 comes from the periodic table. The 7 comes from counting up the number of electrons from this structure. And so 6 minus 7 is minus 1. You would predict this, in this molecule, oxygen will have a minus 1 formal charge. And indeed it does here. Oxygen needs a negative charge next to it in order for this molecule to be written correctly. And so you can go over some of these formal charge calculations in order to practice. The polar covalent bonds, are figured and analyzed using the electronegativities of the atoms. Remember, the electronegativity is how strongly an atom attracts its shared electrons. You will remember that fluorine has the highest electronegativity and oxygen is second. That fact will become important in organic chemistry because there are so many carbon-oxygen bonds, and you'll need to think about the reactivity of oxygen when it is bonded to these other molecules. The ones that come third are nitrogen and chlorine, and that also becomes important. But fluorine is the highest in electronegativity. Oxygen is second. You can remember generally the electronegativities. It is not necessary to remember all of these values, but you can remember the trends. The electronegativity increases as you go from left to right. Electronegativity also increases as you go from bottom to top in the periodic table. You do need to remember those trends. You probably already remember them from general chemistry. There are 3 types of bonds. Covalent bond, where the atoms are equally sharing the electrons used to form the bond between them. So here, carbon bonded to carbon, the electronegativity difference is definitely going to be less than 5, which is the general cutoff for a covalent bond. A polar covalent bond has an electronegativity difference between 0.5 and 1.7. So you simply look up the electronegativities of these numbers and see what the difference is between them. If the difference is between 0.5 and 1.7, then, and in organic chemistry, most of the bonds are indeed polar covalent bonds, or in the carbon skeletons, they may be covalent bonds. Ionic bonds are where the 2 atoms differ in electronegativity by more than 1.7. This would be an ionic bond. Although sometimes the ionic bonds aren't drawn like this with a positive and a negative charge. In some cases, the bond is regarded as having some covalent character and some ionic character. And the more ionic character the bond has, the more reactive that molecule will be. And so we will see those, especially when we get into the reactions involving organometals, where you have carbon attached to a metal. Electrons tend to shift away from the lower electronegativity atoms. So here, the bond's polarized. So for example, here, the electron density is residing about equally on the 2 carbons. Here, in carbon-oxygen, in a carbon-oxygen bond, the electron density is shifted towards oxygen because oxygen is higher in electronegativity. So this is a polar covalent bond. This arrow shows how the electrons are shifted more and reside more and literally spend more time on oxygen. The size of the electron cloud will be larger on oxygen than on carbon for that bond. Sometimes this is represented by drawing partial positive on carbon and partial negative on oxygen. You can see the greater differences in electronegativities. Here, see, this is covalent, where you have a very small difference in electronegativity. Then polar covalent, where, like this one, is carbon-oxygen, where there is a significant difference in electronegativity. Now we get into the carbon metal and the nitrogen metal bonds. And so, like I said earlier, this is in between polar covalent and ionic. These bonds will have some polar covalent character and some ionic character. It depends on exactly what the metal is. You can change that by changing the metals. And then in molecules such as sodium chloride, there's a large difference in electronegativity. And of course, this is purely an ionic bond. The organometal bonds, here you can see that the carbon has a higher electronegativity than lithium. And so that bond, the electrons in this bond will reside mostly on carbon. The lithium is electropositive and gives up its electron density. And so the lithium here will give up its electron density. That pair of electrons will spend most of its time on carbon, and so carbon can accurately be drawn with a negative charge on it, and lithium will have a positive charge on it. So as I was just saying, some bonds can be drawn as a covalent bond or as an ionic bond. Both of these can be acceptable. It depends on how the molecule is reacting at the time. But when considering the way that molecules react, if the bond that's reacting is a carbon-metal bond, you can consider that carbon to be bearing a negative charge when thinking about the reaction site, reaction speed, or rate, etc. A general chemistry review. Here are the orbitals that you're familiar with: s orbital, a py orbital, and px orbital, and a pz orbital. These are the three p orbitals, all orthogonal from each other and perpendicular to each other. These have wave properties and particle properties also. The 3D plot of the wave function squared gives an image of the atomic orbital, and this is indeed an atomic orbital. The S is round. The p orbital is sometimes called dumbbell-shaped. The electron density here that's shown, this orbital represents where the electron can be found 90 to 95% of the time. So this is really a probability drawing. So actually the electron could be found out here, but most of the time it will be found inside these lobes. So the atomic orbital, what you can think of it as a cloud of electron density. Electrons behave as both particles and waves. Sometimes that can be confusing, but you can select which type of characteristic is needed as in order to explain the observable. The theory matches experimental data and you can also use it to predict characteristics. So you can think of the electron as like a wave on a lake. Its wave function can have a positive value, it can have a negative value, or it can be zero at a node. So what that means is that at this node, there is zero probability of finding the electron at that point. So for example, right here where the node is, there is zero probability of finding the electron at that node. However, the electron density is occupying the space above and below that node, and so we know that the electron does have to pass through that node. So hence the wave nature and the particle nature of the electrons. The orbital regions can also be negative or positive or zero. The zero will be at the node. This has nothing to do with whether you have a carbocation or a carbanion. This is just the region of space. This orbital can occupy one electron or two electrons. And sometimes you'll see these assigned, these lobes, the red lobe, the blue lobe. Sometimes you'll see the lobes assigned a positive charge and a negative charge, or vice versa, negative and positive. It doesn't really matter. It can be assigned red and blue, or it can be assigned green and yellow. It doesn't matter. The only difference, the only thing that's important to convey is that they are different. They are different lobes of this orbital. So that corresponds to the sign of the wave function, not the charge of the molecule or the formal charge on that atom or anything else. So be certain not to get those confused. Electrons are most stable. That's the lowest in energy, or if they are in the 1s orbital. The 1s orbital is the lowest in energy. Then you have the 2s orbital. That's the s orbital in the second period. Then you have the 2p orbitals, and these are still higher in energy. They have equal energy, and so these three are degenerate, but they'll be higher in energy, and that is because the electrons are lying farther away from the nucleus. The closer the electron lies to the nucleus, the lower in energy it is, the more stable it is. So here are some common elements and their electron configurations. I don't think you need to memorize these, but it is good to see them and to know where they are in case you feel like you need to refer to them. So the hydrogen atom has one electron. It will reside in the 1s orbital. Helium has two. Notice they are both in the 1s orbital, and they have equal and opposite spin. Then lithium, another electron is added, and it goes to the 2s orbital. And then beryllium, you have two electrons in the 2s orbital in addition to two electrons in the 1s orbital. And notice these are paired. They have equal and opposite spin in each of these energy levels. So then the next electron goes into a 2p orbital. Then the second electron goes into a different 2p orbital. Then nitrogen, you populate the third 2p orbital. So these are all degenerate. Each one contains one electron. And so here the spins are all parallel and they are not paired. And then oxygen, you pair two of the electrons in one of the 2p orbitals. And then fluorine, you add another one. And neon, you add the third. So now you have the two second period will have the stability of the filled octet, 2, 4, 6, 8 electrons. And you also have the stability of the filled 1s orbital. So neon is very unreactive. It's one of the noble gases. So this completes your introduction to the review of general chemistry, at least the first lecture for it. And we will have 2 more lectures that give you a review, a very rapid review of general chemistry, and it will inform you of anything that you need to go back and look at again.